Okay, so here we go. We're going to talk about, I'm trying to make this a little bit smoother, I think. I pre-wrote some of this, and that should help us a little bit. So we're going to talk about this unified mass unit. So I want you to think about this. We've been talking about the nucleus of an atom for quite a while. And if you look, you can find that carbon has a mass, I don't know, 12.1 something if you look in the periodic table. But we're going to round it to its whole number of 12. That's the common carbon, the most common isotope of carbon, a nuclide with 12 with 6 protons and 6 neutrons. So again, reiterating that nuclide, a specific number of protons and neutrons. So what these scientists did is they said, well, when we're working with with nuclear physics, we're working with little bitty particles. And we're talking about these. It's really rough talking about them in terms of mass in kilograms or grams. So what they did is they said, well, let's create a unified mass unit, or U. And so what they did is they said, well, let's take the mass of carbon, which is 12, and then we know that if that's 1 mole of carbon, 12 grams of carbon is 1 mole of carbon. But if you remember, that's Avogadro's constant, which is 6.02 times 10 to the 23rd atoms of carbon. So if they take 12 grams of carbon and they divide that down here in the bottom, I'll put a highlighter on it, down here, and they divide that by the number of atoms in 12 grams of carbon, then they get grams per atom. And so that when you get that number, you can imagine how small that's going to be. 12 divided by 6.02 times 10 to the 23rd, that's going to be an extremely small number. And if you look here, it actually ends up being this number right here highlighted. I'll put it underneath it, that number right there. And so what they did is they said, well, let's take 1/12 of that, and whatever that value is, which happens to be this value right here, now I put a box around, then 1/12 of that number is this, so that there. So when I did the math here, up here, when I did this math, I got this number down here, if you follow my math here. And they said that is 1U, so I can carry down my 1U. So that's the atomic mass unit. And then we'll base everything else off of that. So we can now talk about things in U's. Oh, hydrogen is 1/12 U. So it's 1/12 of this number because hydrogen has an atomic mass of 1. So anyway, I hope that sort of makes sense. And I think, and then they said, well, now we can put everything in terms of U. So they then said, oh, then from that we can get what a proton is in U. So you have the atomic, remember how in a table of constants you can look up the proton mass, the electron mass, and the neutron mass. Well, now we can convert all these with just a simple factor label problem into U's. So here's the work for the electron mass. I'll put the new writing in blue. So here's the electron mass, and then so this long number right here, 9.1. I took it out to a lot because we are working with U's, and then this is what we found just on the previous page. So that's our factor conversion. And so then doing that math, we got that one electron has this many U's. It's that much of a U, of 1 U. So the unit of a U being 1. And we can do the same for the neutron and the proton. And if you look in your book, they have a nice table where they show you the unified mass unit of each of these at the beginning, page 380 in your book. Okay? So that's the atomic mass unit. So get used to working in U's. And sometimes I get confused by it because the math that we do almost doesn't save you that much. It really doesn't. But it is important to use because eventually, if you get up into the higher parts of this in quantum physics or nuclear physics in this case, then you would use this quite often. All right. So then we get to this thing called the mass defect. Now I'm going to give you an example here. Imagine tomorrow if I called out group hug, and we all got together and we did a group hug. Okay, but now before you think of that, imagine before we did that, we all stepped on a scale and we recorded our weight, and then we took all of our weight and we added it together. So that's and let's call it our mass. And so we added all of our mass together. That's a scalar quantity. We just add it together. Quite simple. And we added it all up. But then we had this huge scale, and I said, group hug. And we all got on the scale, and we did a group hug on this big old scale. And we looked at the mass. We would find that, and this is weird in the quantum world, down there in the nuclear world, things are a bit different. That our mass together is less than our mass individually. Now, that's weird, but that is true. And so what they've found out is that they'd call it a mass defect. Like, where did that mass go? You know, I mean, they don't really know where it went, but so eventually they started studying it and looking at it, and they came up with this concept called the mass defect. And so they found out that the mass of the nucleus, I'm getting ahead of myself. If we wanted to get just the mass of the nucleus, we would take the mass of the atom, and we could look that up in the periodic table if we wanted to, and then we would multiply, and we'd subtract from it the mass of the electron. Now we could do all this in U's if we wanted to, or kilograms if we wanted to. U's might be nicer. So they said, well, where did this mass go to? How do we weigh these things individually? And they weigh more than when they're grouped together as a nucleus. How does that happen? And so it came out to find that they came up that there must be some energy needed to hold the nucleus together. Energy is needed to hold the nucleus together. And you can sort of come up with this right here from this classic equation. You guys all know this as Einstein's classic equation of E equals mc squared. And so the energy, so where m is the mass and c is the speed of light squared. And so it shows, this basically just shows that mass can be energy. So they're interchangeable. And so some of this energy went into holding the nucleus together, holding those protons next to the protons, keeping that strong nuclear force, holding it together, neutron-proton interactions, proton-proton interactions, and neutron-neutron interactions. All those together takes energy. And in a way, you could sort of think of it that way. If we're doing this group hug on this scale, we'd have to sort of hold on to each other to stay together and not fall apart. And so that sort of takes a little bit of energy. I hope that helps you understand what mass defect is and what binding energy is. So the mass defect down here, and we're going to use it sigma here, is, I'm hoping I got I'll correct it if I'm wrong tomorrow, is equal to this sigma minus the mass of the nucleons. It equals the mass of the nucleons minus the mass of the nucleus. Now notice what I said, the mass of the nucleons. So that means you would literally have to go and add all these together, all the nucleons together, and then subtract it from the mass of the nucleus. Now, that may sound sort of crazy, so what you can do is the periodic table is nicely put together for you, and you can get the mass of the atom, the mass of the nucleus from the periodic table. So if you could get just the mass of some of the nucleons, you can put this together quite simply. Okay, and we'll do some problems with this, but again, here's what I'm trying to tell you, is that if you took the mass of the nucleus, that would be us standing on the scale, right? That is less than the mass of all of us together. So this is all of us added up individually. We all stood on the scale separately, individual, and this is together, right? Nucleus and nucleons. Remember, nucleon is a proton or neutron that resides in the nucleus. And so if you took the difference in those, that would be your mass defect. Okay, and so some of that mass was converted over to energy to hold the atom together. And we'll wrap up here with just a little bit of synopsis here of the binding energy. From your book, not doing too much more in your book, the binding energy is the work required to completely separate the nucleons of a nucleus. So, but in general, basically, if you took one proton, for instance, and you pulled it away, and you completely separated it, and then you said, oh, it took X amount of energy to do that. And then if you said, oh, well, therefore there's 100 particles in this nucleus, so if I multiply this number that I just got, the work required to move that 1 times 100, I'd basically have an approximation of the binding energy. But another way to look at it is down here, and that is that mass defect, think about it that way. The mass defect divided by the number of nucleons would also be the binding energy that needed, for a whole atom. So a pretty simple little equation there, um, and and so anyway, if you want to get that into energy, you would just take energy is equal to the mass defect times c squared, because remember, that's mass. So that's just a restatement of this equation. So these are both mass, units of mass. That's mass defect, and this is just the mass in general. So guys, I'm going to stop right there. So I've covered basically only the first 2 pages, but I wanted to go pretty slow with this. This chapter is only about 3 or 4 pages, maybe about 5 pages long. We'll stop right there for the night and let you absorb that. So basically the first 2 objectives have been covered. Okay? Good night.